All right, so this is going to be the Ed puzzle on projectile motion. For students who are in class, we'll be going over a lot of this in class. If you are absent, I'll ask you to do this Ed puzzle, or if you're VLA, I'll ask you to do this Ed puzzle. So characteristics of projectile motion. This is just a little mark to let me know how far I can write when I'm making this. First of all, the only force is gravity. So that's it. Now, the amount of gravitational force will depend on an object's mass, because we know force of gravity is basically the object's weight, and that's m times g, which is the acceleration due to gravity, which is 9.8 meters per second. Again, you could always round to 10 meters per second. At any rate, that's the only force. Therefore, the horizontal motion is constant. Now, what that means is, of the kinematics equations we've had, the only one that works with that is this. If you recall, we said that average velocity is equal to change in position or displacement over change in time. Instead of calling this V average, I'm going to call this VH for horizontal. It's the same equation. Guess you can read that okay. Nothing different than that. We also have the implication that with vertical motion, since there is gravity and it always acts down, the vertical motion changes at a rate of 9.8 or 10 meters per second. So therefore, the other linear motion equations that we have could be used here. For example, we know that acceleration is equal to change in velocity over change in time, Vf minus Vi over delta t. And there's a couple other rearrangements of that. The acceleration would be 9.8 meters per second. And these velocities would always be vertical velocities or vertical components of velocity. Again, if we're thinking about there being acceleration, we're only thinking about vertical information. Constant velocity, only horizontal information. So that's one of the formulas that we could use. Another one would be a version of this. It's x, although I guess it could be y, would equal to 1/2 a t squared. If you don't start from rest, that's actually delta x, that's displacement. You could also say, or delta x is equal to initial velocity times time plus 1/2 a times squared. So this is only when vertically we are not starting from zero. The final equation that we have that we can use, we've already used, Vf squared, final velocity squared, was initial velocity squared plus 2 acceleration times displacement. Again, I guess we're thinking vertically, all these x's should probably be y's, as in the letter y, not y's like smart. But we've used x's so much, I think I'm going to keep that consistent here. This is an equation we've already had. This is an equation we've already had. We've already had this, and we've already had that. So I'm going to go now and do a sample problem. I'll put it over here. So I'm going to end up doing 3 sample problems. A lot of times we'll do things where we have only horizontally launched projectile. That's a little simpler type of motion. So this sample, 1A, band director, say teacher, throws a trumpet horizontally off the 8.1 meter tall band tower It lands on a student (16.5 meters away). And the question is, what speed thrown, or what's its initial velocity. The first things I always do with most of these type of problems is draw a picture. I don't have a ton of room to do that here, but I'll try. So let's say I have something like this. Here's my band tower. Something like that. Throwing a trumpet. So it's going to land on a student over here. Oh no, they're impaled. So this distance, 16.5 meters, this height, and I did not draw it to scale, 8.1 meters. It does help me to think about things. So one of the things I'll normally ask people is, do you want to start by thinking vertically or horizontally? Well, if we know that the person threw the trumpet horizontally, it makes sense that this initial velocity we're trying to figure out, the speed with which it was thrown, is going to be a horizontal velocity. So you're probably saying, I'm going to think horizontally first. Good call. Well, the only equation I've got for that is this one. VH, which actually would be the speed it's thrown, was change in position or change in time. And you might say, well, what do I use for delta x? Is it 8.1 meters or 16.5? This is a horizontal equation, so we can't just shove a number in. It's something that's vertical. So we're going to use 8.1 meters for vertical situations. Here we're going to use 16.5. So that's going to be 16.5 meters over, wait a second, what is delta t? I don't know that yet. So the problem is in order to solve this horizontal equation and get my answer, now I've got to go back and think vertically. So I really need to find time. Of my vertical equations, I've got 3 of them here that I could use. This doesn't even have time, so I can't use that. This one does have time, and this one has time. But I don't know any velocities. Well, I guess I know that my vertical velocity at the beginning is 0 because it's launched horizontally. But I don't know my final vertical velocity. I do know my acceleration, but I don't know time. So again, I've got 2 of 4 things I don't know. That's not helpful. Here, since my initial vertical velocity is 0, I don't have to use this complicated version of the formula. I can use the simple version of it. I think that's what I'm going to do. So I'm going to change this as I'm thinking vertically. I'm going to call it delta y. 1/2. That's fantastic. T squared. So this delta y, now I'm using vertical distance, which is 8.1 meters. 8.1 meters, and I'm going to have 1/2, 9.8, and then times squared. So 8.1 over 4.9. Let's put a t squared, 1.65. Let's put a t squared. The square root of that, t is equal to 1.29 seconds. So now I'm going to go and bring this back up here. So it's 16.5 over 1.29 seconds. That is equal to 12.8 meters per second. Okay, so that is something that I needed to end up. Even though this seemed like a pretty simple thing to do, I didn't know the time and I had to think vertically to get that. So that's why projectile problems can be a little more difficult. You've got to treat the vertical and horizontal parts independently. So that's problem 1A. Hopefully that works out well for you. So this is sample problem 1B. It looks like 18, but it's really 1B. Very similar to the first one. I want to show you how the horizontal projectile problems can be rearranged slightly and how you have to solve them a little bit differently. So in this case, we've got an owl. It's up here in the tree, spitting out a pellet, pardon me, not me, horizontally at a known speed of 7.5 meters per second. The pellet lands on the ground 3.1 seconds later. We don't know how high the nest is, and we don't know how far it goes. Those are the two things we're going to want to figure out. Like normal, I'd like to draw a picture. So there's the owl spitting it out sideways 7.5 meters per second, and it lands on the ground 3.1 seconds later. So the first thing I'm going to need to do to find out how high the nest is, I need to think vertically. So to think vertically, I'm going to use one of these equations. So it has acceleration in it. We know that's still 9.8 or 10 meters per second squared. So in this particular case, I'm going to say delta x equals 1/2 at squared. There is no vertical velocity at the beginning of this. So that delta x, 1/2, 9.8, 3.1 squared. Okay? So in this case then, and again, that should really be delta y, but ends up being 47.1 meters. That is a very tall tree, probably out west, around 150 feet tall. So maybe one of the great redwoods or something like that. The second part of this is going to be asking how far away from the base of the tree does the pellet land. So in this case, we're looking at a horizontal distance. So there's, again, only one horizontal equation. It's this. VH is equal to change in horizontal position over change in time, or time interval. So at this point, I've got to rearrange it to solve for this delta x. So a little bit of algebraic rearrangement. Delta x is equal to my horizontal velocity, which is told as 7.5 meters per second. And we're going to look at that 3.1 seconds. So obviously my drawing is not to scale. That ends up being 23.2 meters. And that's that problem. I'm going to do one more, and hopefully that'll wrap it up. Most of the problems that I'm going to assign you, and then most of the things we're going to look at in a first-year physics course are these horizontally launched problems. So sample 1A and sample 1B should really help you out a lot. I will ask you to do one or two angle launch projectiles, and that's what I'm going to do next. So this is going to be an angle launch projectile. It's sample 2. It's going to take a little longer than the second one. Or sample 1B, I guess. So we've got a student here. They're kicking a soccer ball at an angle 28 degrees above the horizontal. The ball has a mass of 0.5 kilograms and is kicked at 40 meters per second. The first thing I'm going to ask you to figure out is to find the vertical and horizontal components. Even if you're not asked to do that in a projectile problem, you probably should if it's an angle launch projectile. So find vertical and horizontal components of the initial speed. So that's an initial velocity. Actually, I should say velocity. That's an initial velocity here of 40 meters per second. But some of it's going vertical and some of it's going horizontal. In reality, obviously, it's going at a 40 degree or at a 28 degree angle. But the whole point of this is to recognize that vertical and horizontal components are independent of each other for projectile motion. The equations we use are independent of each other. Vertical equations have acceleration, horizontal equations don't. So I'm going to draw a picture. It's going to help me out, even though I know my pictures aren't very good. So I've got someone here kicking soccer ball like that. I don't know how a soccer ball looks. There's like check patterns on it. And that is the 40 meters per second. And this is going to be a 28-degree angle. So what I could think of is I could say that I've got, that's 40. .8 degrees, that's going to be my vertical velocity, and that component is going to be my horizontal velocity. So if we think back to some of the vector stuff we did earlier in the year, we know that to get this, that's the opposite over hypotenuse. That is a sine function. So the sine of 28 degrees equals VV over 40. So VV is equal to 40 times the sine of 28 degrees. I think I'd want to do that a little differently. So the vertical velocity is going to equal 18.8 meters per second. Upwards. The cosine is adjacent over hypotenuse. You could use Pythagorean theorem or another way to get the horizontal component. Right now, I'm just going to stick with this. So the cosine, 28 degrees, is equal to VH over 40 meters per second. So I'm going to say VH is equal to 40 multiplied by cosine of 28 degrees. I don't know why I'm using parentheses, kind of weird. Probably should do that here. Okay. And therefore VH is going to be bigger. It's going to be 35.3 meters per second. So those are kind of important. If the projectile lands at the same height as it's launched, so meaning it comes back to ground level in this case, we're going to end up having some symmetry. So that means that this thing is going to go like this. It's going to come back down over here. And that doesn't look very symmetrical, but it should be. So remember, for a lot of projectiles, we want to think about maybe the first half of the problem or the second half of the problem. They use symmetry to get us our answer. So one question I might ask here is, at what rate does the vertical velocity change? Well, that is 9.8 or 10 meters per second every second. At what rate does the horizontal velocity change? I'm going to put the in one of these and not the other. Well, that is 0 meters per second. So there is no acceleration horizontally. There is an acceleration due to gravity vertically. That's what a projectile is. So assuming this soccer ball lands back at ground level, what amount of time is it in the air? So how much time in the air? I'm going to have to solve this by thinking vertically. And the reason is, if you recall, I only have one horizontal equation. And that basically is VH is equal to change in horizontal position over change in time. If I don't know my time, I do know my horizontal component of velocity, that's this, but I don't know how far I go either. There's nothing I can do with that. So if I want to find out how much time it's in the air, I could think about using a vertical equation. Now you could think about half the trip up or down, or you could think about the whole trip. If you think about the whole trip, remember upwards would be one direction, downward would be another, so you have to pick one direction as positive and the other one is negative. I think what I'm going to end up doing is thinking about, say, half the trip, because I also know that at the tippy top of the path, the vertical velocity is equal to 0 meters per second at the top. I know my vertical velocity starts upward at 18.8 meters per second. Therefore, the final vertical velocity will be downward at 18.8 meters per second. So there's a couple ways we could do this. I'm going to use the formula A to put a change in vertical velocity over change in time. Why does it have to be vertical velocity? Because we only have acceleration in the vertical direction. So in this case then, I could say Vf minus Vi over delta t. If I rearrange that, I could say A, come back over here. Oop, I don't want to do that, pardon me. I could say T, time, is going to change in vertical velocity over A. So that's just an algebraic rearrangement of this. So I could think of the downward part of this, the second half of the trip, where acceleration is down and vertical velocity is down. My final vertical velocity over A. Final vertical velocity will be the same as the initial vertical velocity, 18.8 meters per second. The vertical velocity at the very tippy top, which is my initial vertical velocity for the second half of the trip, is 0. And the acceleration is 9.8 meters per second. 18.8 divided by 9.8 gives me 1.92 seconds to fall. That's not the total answer yet, because that's only the time for that half of the trip. I need to find the time for that half of the trip. All right. T total T up plus T down. Well, that's going to be twice this. Because if it's landing at the same height, again, we've got symmetry in the problem. So that's going to equal 1.92 plus 1.92 plus 3.84 seconds. And that's it. One of the other questions you could tend to get here would be to find out the horizontal range, the total distance that the soccer ball travels. Find horizontal displacement. Well, to find that, we're going to go back to the only horizontal equation we have, and I'm going to already rearrange it, because VH is equal to delta X over delta T. Rearranging it, delta X equals VH times T, and this T, that doesn't even look like a T. This time is the total time, because it's moving horizontally both on the way up and on the way down. So delta X is equal to this horizontal velocity, 35.3 meters per second, times 3.84 seconds, should be somewhere around 140-ish, and it's 136 meters. So notice, all this is horizontal information. I'm not using the 18.8, I'm not using the 40. In fact, we only really use that 40 to get the horizontal and vertical components. This was a vertical equation right here, because to figure out the time up and the time back down, I needed to think vertically, because my velocity is only changing vertically. The last thing I could ask here, hopefully I can have room to do this, is I want to find the maximum height. Of the soccer ball. So that's going to happen right here. So the easiest way to think about that, I think we did something like this with the ball toss slab or with one of the linear motion problems, is let's take the simplest equation we can, and let's think about that soccer ball just falling directly down. It doesn't matter that it's moving sideways at all. All that matters is that it's falling. So I could use the simplest version of the displacement acceleration formula, which is delta x equals 1/2 a t squared. Well, what t would I use, though? I'm actually going to only use this time, because that's the time it's falling from the maximum height. And therefore, that will allow me to know the maximum height. If I use 3.84 seconds, it's acting like it's either falling for 3.84 seconds or rising for 3.84 seconds. It's not. That would be much more. That would actually be 4 times the correct answer. So in this case, I'm going to say t 1/2 squared. So this delta x, or it's really delta y because it's vertical, 1/2, 9.8, 1.92 seconds squared. 1.92 squared is about 4. 4 times about 5 is 20. It's going to be a little less than that, so 19-ish. Oh, 18-ish. 18.0 meters. So as you can tell, the angle-launched projectile problems are definitely more challenging. However, it's really the same type of things you can ask. Split up the horizontal and vertical, the velocity into horizontal and vertical components. Find the horizontal range that the projectile travels before it hits the ground. Find the maximum height, and then find the time in the air. Really, it's always these types of things. So this is one of the few cases with the linear motion formulas where you probably can, I don't want to say memorize how to do it, but you can see a pattern a lot more clearly. And there are other ways to do this, but this pattern works almost always. So that's a pretty good one. Hopefully these help you when you go through the problems.